AQA A-Level Physics, Paper 1, 2018 solutions. The questions are not displayed here, but there's a link you can download and follow the question through. Question 1.1 says we should determine the force decelerating the vehicle 2 seconds after entering the escape lane. So we're given the mass, and that mass is 1.8 times 10 to the power 4, and we need to find acceleration, and then we need to find the force. To find the acceleration, we drew a tangent at 2 seconds, and we then pick 2 points from the tangent, and those 2 points is point number 1 and point number 2. And so I can find the acceleration, A equals to the V over the T, and that can be written as V2 minus V1 over T2 minus T1. V2 is 0 meters per second, V1 is 15.5 meters per second, and T2 is equals to 5.8 seconds from the graph, and T1 is 0. So if I populate the equation with the V2, which is 0 minus 15.5 over T2 is 5.8 minus 0, and that will be minus 15.5 over 5.8, and so acceleration equals, we got 2.67 meters per second. Now to find the force, so I can say F equals MA, and M is 1.8 times 10 to the power 4 times the acceleration 2.67, and that equals 48060 newtons. And so we can write the force to be 4.8 times 10 to the power 4 newtons. And we've got negative here because that's negative, and this is deceleration. And the question is to determine the force decelerating the vehicle 2 seconds after entering the escape lane, and that force is this. Question 1.2 says that we should deduce whether a lane of length 85 meters is long enough to stop the vehicle, assuming that the engineer's graph is correct. We cannot use SOVAT for a variable acceleration graph, velocity time graph, but we can use SOVAT for a constant acceleration or deceleration graph. So this one is good for SOVAT, that's not good for SOVAT. So therefore, we have to calculate we have to count the area under the curve here. So 1 square is 2.5 by 1. And so the area would be 2.5 meters per second times 1 second. Seconds cancel seconds, so we get the area to be 2.5 meters, and that's the diameter, that's the distance. And because we've got 22 of the little boxes, so total area would be, or total distance would be equal to 22 times 2.5 meters, and that gives 55 meters. So the distance is 55 meters, therefore 85 meters of escape lane is long enough. Question 1.3. Discuss the energy transfer that takes place when a vehicle is decelerated in an escape lane. Kinetic energy of the lorry is transferred to kinetic energy of gravel as it is pushed aside or moved. The potential energy of the gravel as it may be ejected upwards transfer to thermal heating energy or internal energy or heating of gravel or ground or lorry, work done on gravel or vehicle increasing internal energy or raising temperature. Question 1.4, we now need to work on escape ramp inclined at an angle of 25 degrees to the horizontal and is 85 meters long. We need to deduce whether this escape ramp is sufficient to stop the vehicle. So here's the escape ramp, and we need to, first of all, here we'll have a maximum kinetic energy, and as it climbs up, it's converting the kinetic energy into potential energy. And so here will be the maximum potential energy. We know kinetic energy is a half mv squared, and that equals mgh. So first of all, we need to find the h here, the height for potential energy. So using SOHCAHTOA, I can say sine 25 degrees, and that equals to opposite, which is h over hypotenuse, and that's 85. And so now we can find h. So h equals 85 sine 25 degrees. And therefore, h will be equal to 35.9 meters. So now if we equate these two together, the m cancel out, and I can find the value of h here. If this value of h equals to the value of h, we can compare those two together. So I've got a half mv squared equals to mgh, but the m cancel out. So I get v squared equals to 2gh. I want to make h the subject here. So h will be equal to v squared over 2g. So the v I'm using the v, which is 17.5, the maximum v. So therefore h equals to 17.5 squared over 2 times 9.81. Therefore h will be equal to 15.6 meters. So the escape lane will be long enough to stop the vehicle. So 15.6 meters is around there, and which will be here. So the vehicle will be stopped here. It wouldn't even get to the top here. And here will be 35.9 meters. So the escape lane would be long enough. Question 1.5. We need to discuss whether an escape lane containing gravel or an escape ramp would provide the safer experience for the driver of the vehicle as it comes to rest. The straight road of uniform gradient, because the deceleration is uniform. With the gravel, the initial deceleration is large and may vary. Traveling through gravel could make the vehicle unstable or bounce erratically. Gravel, because on the ramp, the lorry would roll backwards after stopping as it has no brakes. Question 2.1. The table here shows results of an experiment to investigate how the de Broglie wavelength lambda of an electron varies with velocity. So in question 2.1, show that the data in the table here are consistent with the relationship that lambda is inversely proportional to the speed. Okay, so if lambda is inversely proportional to speed, we can say lambda equals k times 1 over speed, which can be written as lambda equals k over v. So if I make k the subject, so now we can say k equals to lambda v. So now what we need to find out is to multiply these two together. That's lambda and k, multiply them together, lambda and v, and we check or we compare the value of their k values here. So here I'm going to put here k, and so when I multiply these two together, I should get the value of their k's. So 1.5 times 4.9, and I get 7.35, well, times 10 to power minus 4, and the unit will be meters squared per second, because the velocity is meters per second, and this is meter. Meter times meter is meters squared, and then per second. So the second one is 7.25, and the third one is 7.35. So these two are very similar. This is slightly different, and therefore the value of k is relatively constant. Not constant for that, because you can see it's not the same as that, but these two are the same. So we can say yes, relationship is true. Question 2.2. Calculate a value for the Planck constant suggested by the data in table 1. Alright, so the de Broglie wavelength, lambda, is h over p, where p is the momentum, h is the Planck constant. And so we can then write that lambda equals h over mv. And if I multiply lambda times v, we get the h over m, which is what we call the constant. So our constant that we calculated is k, so therefore we know that k equals h over m. But we need to calculate a value for Planck. Alright, so Planck constant is equal to k times m. So here is the value of our k value. And so if I take that and multiply by the mass of electron, I can find the value of Planck constant. So let's do it for both of these values. So for k equals to 7.35 times 10 to power minus 4, then h will be 7.35 times 10 to power minus 4 times the mass of electron, which is 9.11, times 10 to power minus 31 kilogram. And that value will give 6.69 times 10 to power 6.69 times 10 to power minus 34 joules seconds. So that's the Planck constant value. But if we use k equals to 7.25 times 10 to power minus 4, and then we can find the h will be 7.25 times 10 to power minus 4 times the mass of electron, 9.11, times 10 to power minus 31. And so that value gives 6.0 times 10 to power minus 34 joules seconds. So those two values are the values of Planck constant, which is that they're very close. So either value is fine. Question 2.3. Explain how the pattern produced on the screen supports the idea that the electron beam is behaving as a wave rather than as a stream of particles. So here is the electron diffraction tube, and this is the pattern that it produces. So this is the bright spot here, dark spot, bright spot, and bright spot. So that's the first one, and then second and third. And so this is symmetrical here. Particle behavior would be only produce a patch or circle of light, or small spot of light, or particles will scatter randomly. Wave property shown by diffraction or interference. Graphite causes electron waves or beam to spread out, or electrons to travel in particular directions. The bright rings, where maximum interference occurs, where waves interfere constructively or are in phase. For a diffraction rate in maxima, when sine theta equals n lambda over d, where d is spacing of atomic layer in crystal. So d is spacing of atomic layers in crystals. Question 2.4. We need to explain how the emission of light from the fluorescent screen shows that the electrons incident on it are behaving as particles. Electrons must provide enough kinetic energy instantly to cause the excitation, the atom or energy transfer in one-to-one interaction. Electron can provide the energy in discrete amounts. Energy cannot be provided over time as it would be in a wave. Idea of light emission due to excitation and de-excitation of electrons or atoms. Idea of collisions by incident electrons, moving electrons in atoms between energy levels, shell or orbits. Light or photon emitted when atoms or electrons de-excited or electrons move to lower energy levels. Question 3.1. Explain how a stationary wave is produced when a stretched string is plucked. Waves travel to the boundaries and are reflected. Two waves traveling in opposite directions interfere or superpose. Fixed boundaries cannot move, so are called nodes. In some position, the waves always cancel or interfere destructively to give zero amplitude or no vibration, or nodes. Interfere constructively to produce positions of maximum amplitude or maximum vibration, or antinodes. Question 3.2. The vibrating length of one of the strings of a violin is 0.33 meters. When the tension in the string is 25 newtons, the string vibrates with a first harmonic frequency of 370 Hz. Show that the mass of a 1 meter length of the string is about 4 times 10 to the power minus 4 kilograms. So we have the length 0.33 meters. We got tension is 25 newtons. We got mu, and that's the mass per unit length, and we're looking for that. Frequency is equal to 370 Hertz, and V, the velocity in a string, is equal to root tension over mu. Because the question is referring to first harmonic is what we call the fundamental, and that's the first harmonic. And what that implies is that we have a length, and the first wave of the first harmonic will be that distance, which is L, will correspond to lambda over 2. So for first harmonic, lambda will be 2L. Also, we know that V equals F lambda, and so we can make F the subject, F equals to V over lambda. But because we know what V is, so we can rewrite F to be root T over mu times 1 over lambda. That's F. Therefore, we can say F equals to 1 over 2L for first harmonic root tension over mu. But we're looking for mu. So if we, to find mu, we can say F times 2L equals to root T over mu. So if we square both sides, we get 4F squared L squared equals to T over mu. So therefore, mu will be T over 4F squared L squared. So we now need to plug in those values to find the value of mu. So T is 25 newtons over 4 times the frequency 370 squared times the length 0.33 squared, and that's mu. And when we work that out in a calculator, mu turned out to be 4.19 times 10 to the power minus 4 kilogram per meter. So that means we know mu is m over L. So for 1 meter, mu will become 4.1 or 4.2 times 10 to the power minus 4 kilogram. So that will be so that will be the mass. So the mass will be 4.19, or we can say the mass is 4.19 times 10 to the power minus 4 kilogram for 1 meter. And that's what we're looking for. The mass equals 4.2 times 10 to the power minus 4 kilogram. Question 3.3. Determine the speed at which waves travel along the string in question 3.2 when it vibrates with a first harmonic frequency of 370 Hertz. Well, we know the speed in a string is root of T over mu, and we know that mu is 4.19 times 10 to the power minus 4, and T is 25 newtons. So we can say V equals to root 25 over 4.19 times 10 to the power minus 4, and that gives 244 meters per second. And so that is the speed. Question 3.4. We need to determine the higher frequency that is produced when the string is stretched by rotating the turning peg through an angle of 75 degrees. We need to assume that there are no change in the diameter of the string. So here's the graph, and for 25 newtons, if you look on that graph, you will see that the extension will be 11 millimeter, and that's the extension there, and the tension for 25 newtons. The frequency for that is 370 Hertz, and the diameter is 7.02 millimeter. So for 1 rotation of the peg, we have a circular rotation, and the circumference of that is pi d, or you can say 2 pi r. And what we now need to do is work out the diameter, the circumference. So what we need to do is work out the circumference for that, and the circumference will be pi d, so that will be 7.02 the diameter times pi, and that gives 22.05 millimeter, and that is corresponding to one rotation, which is 360 degrees. So 360 degrees gave to 22.05 millimeters. 1 degree we give 22.05 over 360, and for 75 degree rotation that would be 22.05 times 75 over 360, and that gives 4.595 millimeter. So the total extension will be 11 plus 4.6, and that equals to 15.6 millimeter. And so if we go on to the graph and check for 15.6 millimeter, and that will correspond to, and if we come here and check from 15.6, and that will correspond to here the value of 35 newtons. So that is 15.6. So now we have the first tension is 25 newtons, and the frequency for that one is 370 hertz. And now we got the second tension, and that is 35 newtons, and we need to find the frequency for that. But the relationship between frequency, because we know frequency is directly proportional to root of tension from the formula where frequency equals 1 over 2L root T over mu. So you can see frequency here, root of frequency is proportional to root of tension is proportional to frequency. So that's what this is. So which means that we can say that frequency is equal to K root T. And I can then say, well, or I could say F squared is equal to KT, because I square, what I've done is square both sides. So I get F squared equals capital T. And from there, I can then write the constant value. So K equals to F squared over T. So what I meant is, if I have F1 squared over T1, that will be equal to F2 squared over T2. But I'm looking for T2, so I can make, but I'm looking for F2, so I can make F2 the subject. So F2 squared equals to F1 squared times T2 over T1. And I can then go on by saying F1 or F2 would be equal to square root F1 squared times T2 over T1. So that would be square root 370 squared times T2, which is 35, over T1, which is 25. And that will give, by multiplying that out, so that's F2. And F2 will be equals to square root of 191660. And that equals to 438 hertz. So the higher frequency produced, F2, is equal to 438 hertz. So that's the higher frequency. Question 4.1, we need to determine the area of cross-section of the wire that has been used for the resistor. So these are the values that have been given. So I need to find the area But before then, I need to find the length. So I know the length of wire is going to be L is going to be 50 tons, number of tons, times the circumference, which is pi d. And that will give 50 times pi times d, and the diameter is 0.008, and that gives 1.26 meters for L, the length of the wire. Applying resistivity in this case, so we know that rho is equal to RA over L, and I can find that the A I'm looking for, so A, the area, so A, the area is going to be rho L over resistance, and I know the rho is 4.2 times 10 to the power minus 7 times L, 1.26, divided by the resistance, which is 250, and that gives the value of A to be 2.11 times 10 to the power minus 9 meters squared. So that's the value of the cross-section area. Question 4.2. The students select a resistor rated at 0.36 watts for the 0.25 kilo ohm resistor. Determine whether the resistor is suitable. Okay, so we know P is equal to 0.36 watts, and we know that R is 250 ohms, and applying P equals to V squared over R, I can now rewrite this and find the value of P for that, and the value of P for that is 9 squared over 250. From the diagram we got 9 volts, and therefore P equals 0.32 watts. So the resistor is suitable. Another way of doing this is to find V, because we know P equals V squared over R, therefore V squared equals PR, which implies V equals root of PR, and that will be equal to root of 0.36 times 250, and therefore V equals 9.5 volts. So 9.5 volts is the dissipated voltage, but the actual voltage is 9 volts, and which is the voltage that is available. So this will not dissipate at 0.36 watts. So we can say will not dissipate at 0.36 watts, because it will only dissipate at 0.32. Question 4.3. Determine the value of R that the student should select. Give your answer to an approximate number of significant figures. The question asks us to determine the value of R that the student should select. We also need to give the answer to an appropriate number of significant figures. So what we need to say now is that the ratio of resistance is equal to ratio of voltages, and in this case this is one part we want to look at, and we want to look at that one here. So we got the two section. The first one here, we're going to call that one the R1, and this bottom here will be R2. Right, so we can then write that R2 over R1 must equal to V2 over V1, and so therefore R2 will be equal to V2 R1 over V1.
So R2 will be equal to V2 is 5 times R1, which is 250. We need to divide it by V1, which is 4. As you can see, therefore, R2 will be equal to 313 ohms. So if that's R2, now because R2 is R and 750 in parallel, so we can then say the 1 over R2, which is the R total, will be equal to 1 over R plus 1 over 750, because these R and 750 are in parallel, which is R2. So now we can write the R2 in that sense by saying 1 over 313 will be equal to 1 over R plus 1 over 750. So 1 over R will be equal to 1 over 313 minus 1 over 750, and that equals to, now, so if we use our calculator, we should get 1 over R equals to 7 over 3750. Therefore, R equals to 3750 over 7, and that equals to 535 ohms. And that implies that R is roughly equals to 540 ohms.
Question 4.4. We need to state and explain the effect on the output PD of increasing the temperature of the thermistor. Resistance of thermistor decreases, the output PD decreases since resistance of the parallel combination or circuit decreases. Lower proportion of PD across the parallel combinations or higher proportion across 250 ohms. Higher current, so greater PD across the 250 resistor. Question 5.1. We need to show that the linear speed of the acrobats is about 4.5 meters per second. So here's the diagram, and these are the acrobats here. And so we've got this angle here, and we have to use something called secateurs because we need to find the radius from there to there. We already know from there to there is 1 meters, but we need to find this from there to there. And once we find this, we can add it to 1 meters. That will be the radius. So we can use something called secateur and tan of an angle theta. This angle here is opposite over adjacent. We know the height here. The height is 5 meters. So if we just put the height there, from there to there, it's 5 meters. And then so we then need to write the tan, which is opposite, and opposite is what we're looking for. Let's call that D over 5, and that implies that D will be equal to tan theta 5, but we know what theta is, 28.5, so that'll be 5 tan 28.5. That's D. So this little bit here is D, and we can then find what that D is. So that gives us 2.715 meters. So to find the radius R, the radius R would then be equal to D plus 1, and that would be 3.715 meters. Now I can use the radius to then find the velocity. So velocity will be equal to 2 pi r over
T, and that equals to 2 pi times 3.715 over 5.2, and that gives 4.49 meters per second. So that's the linear velocity. So this is the same diagram, but looking from the plan from the top, you can see that's this bit here, and this is 1 meter. So if I put it there, 1 meter, and that's 1 meter. And so I've just extended this bit here, just raise it up, and that's the angle. So that's the D I was looking for, and the radius is from there to there. So that's the radius. So I found the D, and then I add 1 to get the radius, and that is what's giving us centripetal force.
Question 5.2. We need to determine the tension in each rope that supports the acrobats. So the tension will be, if we basically draw,
we can do it in 3 ways.
but
You got the acrobat here, that's the weight mg,
and
that is the tension, and that angle
is
28.5 degrees, and that too will be 28.5 degrees. So we can find the vertical force here.
And so that tension should be equal to that vertical force.
And if I resolve this using cos of an angle theta, will be, remember this one here is the tension, so that's the tension there, so that's T. So this cos is adjacent over hypotenuse, and the adjacent is FV over hypotenuse tension. So therefore, I can write FV equals T cos theta, but FV is mg, so we can then say, well, mg equals to T cos theta, and so I could write that as mg equals to T cos 28.5 degrees. So what is T then? T will be equal to mg over cos 28.5 degrees, but the mass is 85 times 9.81 over cos 28.5 degrees. Therefore, T will be equal to 949 newtons, which is roughly 950 newtons. But there are other ways you could have done it. So we could have done it using what we call the centripetal force. So we could have done it by saying FH, because that would be the centripetal force here. So that's FH, H for horizontal, because the acrobat is there. So, and that FH will be mv squared over r. But I do know that m is 85 times the velocity, which is 4.5, we calculated that earlier, squared, and over 3.71 for the radius that we got earlier. So if we work that out, that would be 464 newtons. But we also know that the weight of the object, mg, is equal to 85 times 99.81, and that equals to 834 newtons. But we can apply the mg here, the fh there, that's mg, and the tension here, so that's a right angle triangle. So we can then say, well, T squared is equal to W squared, the weight, plus FH squared. So T squared will be equal to 464 squared plus 834 squared. T will be square root of that value there. So that will be 834 squared plus 464 squared, and that gives 450 newtons. So you can calculate it that way. Another way we could calculate it is to find another way to calculate it is to resolve the horizontal force by using sine theta will be, so if you look at that, you can see that this is 28 degrees here, and if you resolve this one, this is the horizontal force, which is FH. So sine of that is opposite over hypotenuse. So we can write that down as opposite, which is FH over the tension. And so FH will be T sine theta. And so we can find T now. So T will be FH over sine theta. And we know what FH is. We've already worked that out. That's 4. So that would be 464 over sine 28.5 degrees. And if we do that, we then get T to be equal to, so T will be equal to 970 newtons. So the answer is between 950 to 970 newtons. So that is correct as well. So that is correct, that's correct, and that's correct. So you can choose any of the 3 methods to do it. Question 5.3.
We need to discuss the consequences for the forces acting on the pole when one acrobat has a much greater mass than the other.
Vertical force on the pole increases. Increase mass increases weight, and hence tension in the pole, in the rope, for the same angle. Centripetal force on the acrobat's masses would be different, not equal, and that would be greater on the more massive acrobat. The centripetal force will be greater on the more massive acrobat, traveling at the same speed, same angle to vertical. Unbalanced horizontal forces, resultant forces exist on the pole, and unbalanced moment acting on pole, resultant torque acting on pole, causing the pole to sway or bend or move or tilt or topple the platform towards more massive acrobats.
Question 6.1. State the quantity that is not conserved in an inelastic collision.
Kinetic energy is not conserved in an inelastic collision, but momentum is always conserved in any collision. Question 6.2.
We need to show that the speed of the joined trucks immediately after the collision is about
0.3 meters per second. Okay, so you got the mass of a truck moving in this direction and the B moving in that direction, and that's A. These are the masses and the velocity, and this is the mass of that velocity. And when they stick together after collision, this is what happened. And so, applying the principle of conservation of momentum, the total momentum before collision equals total momentum after collision. Before collision is MA times UA plus MB times UB equals ma plus mb into bracket v. That's the final velocity. Okay, this is the final velocity now. So I'm making v the subject. So I get ma ua plus mb uv over ma plus mb. And this is what I'll get here. ub is minus 3.1 meters per second. So that's minus, and that made this bit minus. And therefore, v equals 0.271 meters per second. And that is roughly 0.3 meters per second. Just about 0.3 meters per second. Question 6.3 states that we should calculate the impulse that acts on each truck during the collision, and we need to give an approximate unit for the result. Alright, so we know that impulse is force times time. At the same time, it is changing momentum, and changing momentum is changing mass times velocity. And so we can write I to be mass times changing velocity, and that mass is going to be final velocity minus initial velocity. And so we can work out the impulse for mass of A. It should be the same for mass of B. So for mass of A, we know that I will be equal to 16,000 into bracket. Final velocity is 0.271 minus initial velocity, which is 2.8. Well, in this case, it's the magnitude that matters, because impulse, so we don't need to worry about the negative. So we will get minus 40464 newtons per second. So the actual impulse we're looking for, the actual impulse we're looking for is 40464 newtons, and that can be written as 4 times 10 to the power 4 Newton seconds. So we can calculate the impulse for the mass of A, and we know that that's going to be 16,000 into bracket 0.271 minus 2.8. And if we punch that into calculator, we get the impulse to be minus 40464 Newton seconds, and that would be 4 times 10 to the power 4 Newton seconds. So we don't need to worry about the negative, we're just looking for the magnitude of the impulse. If we do the same for B, so the mass of B, well, so the impulse would be 12,000 into bracket final velocity, which is 0.271 minus the minus 3.1. So let's just make sure we write that clearly, and that will give an impulse of 12,000 into bracket 3.371. That's times, but don't forget this is going to be plus now, and that gives again 4 times 10 to the power 4 Newton seconds. So that's the impulse we're looking for. 6.4, we need to explain, without doing a calculation, how the motion of the trucks immediately after the collision will be different for a collision that is perfectly elastic. Trucks moves in opposite direction and rebound. Velocity of B is greater than that of A because total momentum is to the right, or B has a lower mass. Momentum of B after collision is the same as that of A before the collision, and vice versa. Question 7. What is the correct unit for the area
under a force time graph?
So the area under a force time graph is going to be force times time, and that is impulse I, and that will be also equal to change in momentum. And for change in momentum, the unit will be mass, which is kilogram meters per second. So that's what the unit will be. And the answer will be B. 8 is asking for what measurement gives the largest uncertainty in the calculation value of resistivity. We know that resistivity is rho equals RA over L. And we know what A is. A is pi d squared over 4 since pi r squared. But r is d over 2. So if you square r, you want to square that. And therefore r squared will be d squared over 4. So we now can replace r to be equal to the resistivity will be R, A, which is pi d squared over 4L. Now, what's going to be important here is if we have 1% of the resistance, 1%, and then we have the length of 1%, and d, diameter is d squared, that would be 2%. So it's B, because B, the diameter, would be the largest, and that's 2%. We need to calculate the specific charge of fluoride ion. So Fi is the fluoride ion, and specific charge would be charge over mass, and the charge here is minus, so it's 1.6 times 10 to the power minus 19, because we've only got 1. If it's 2, then we will say 2 times. If it's 3, we'll say 3 times. But because it's 1, we say 1 times. And so we then need to divide it by the mass. And so the mass in this case will be 19 times 1.66 times 10 to the power minus 27 kilogram. And so if we punch that into a calculator, we get 5.07 times 10 to the power 6 coulombs per kilogram. And so that would be the specific charge for the fluoride ion. And the answer would be C.
So question 10, 2 gamma photons are produced when a muon and an antimuon annihilate each other. What is the minimum frequency of the gamma radiation that would be produced? Okay, so in this case, we've got a muon, an antimuon, so that's a muon, and we've got antimuon, so that'll be, and they give off gamma radiation. So let's just work out the energy here. So E equals HF, and that is equal to mc squared. But the energy of the HF, the mc squared, is actually 106 mega electron volts. So we can say 106 times 10 to the power 6 times 1.6 times 10 to the power minus 19
joules. And when we multiply that together, we get 106 times 10 to the power minus 13 times 1.6. So that's the energy we got in joules. So we now know that the frequency, can be found by saying it's the energy over Planck constant. And so the energy is 106 times 1.6 times 10 to the power minus 19 over 6.63 times 10 to the power minus 34. And when you multiply all that together and divide, and we get the frequency to be 2.55 times 10 to the power 22 hertz. So that would be the frequency, and the answer would be C. 11. We've got, we need to find a quark that represents X. So we have pi plus neutron to give sigma 0 plus X. So we know what pi plus is. Pi plus is up and anti-down, plus neutron is up, down, down, and that to give you, right, we know what sigma 0 is. So sigma 0 is up, down, strange. Now, because we have strong interaction, which means that the strangeness is conserved, so we don't have strangeness here, but we got strangeness here, so therefore X must have anti-strange, so that's anti-S, so that will basically cancel that out to make it conserved. Also, we go up here and we got up here. We have up here, so we need another up there, so we need up there. And let's look at down. Do we have down here? So we got down and anti-down, so that cancels out. Down, anti-down and down cancel out. We got down here and we got down here. So therefore, that's what X is. X is up anti-strange, and that is A. So that's A. Question 12. We've got iodine here and disintegrating. This is a beta minus decay, and then whenever you have a beta minus decay, you always have anti-electron neutrino. So we know that we should have plus anti-electron neutrino. And so the question is asking, what is a property of particle Y? Well, the property of particle Y will be antiparticle. It will be an antiparticle, so that will be B. So that's B. Question 13. From the diagram, it says how many different wavelengths can be observed with incident electrons of this energy. Well, so the energy in question is 2.0 times 10 to the power minus 18 joules. In that case, I can convert that into electron volts by dividing it by 1.6 times 10 to the power minus 19. And that will give us, in electron volt, will be 12.5 electron volts. Since I've got 12.5 electron volts, and I've got this energy level I need to deal with, and the first one is basically minus 3.4 electron volt. This one is minus 13.6 electron volt, and the second one is minus 1.51 electron volts. I have got 12 electron volts, So because I've got 12 electron volts, I could then take away, or I could take away these two energy values to see if it matches my 12. So that difference I need to know. So that would be 13.6 minus 3.4, and that gives me 10 point. What does that give me? 13.6 minus, so let's get 13.6 minus 3.4. I've got 12.5 electron volts, so that's bigger than 10.2, so that's fine. So this is N0, N1, so N1 is fine. The next one I need to go for is the energy difference between this one here. So I have to do 13.6 minus 1.51. So if I do that, I got 12.09 electron volt. I've got 12.5, 12.09, so that is fine. That's fine. So I can do n equals to 2. What about n equals to 3? So with that, n equals to 3 is minus 0.85. So if I do 13.6 minus 0.85, I get 12.75. I don't have 12.75. I've only got 12.5, so I could not do that one. So the only excitation I could do is coming down from there to there, or coming down from there to there, or coming down from there to there. So that's 3 excitations, and that's B. So 3 excitation is B. Question 14. We need to find the maximum kinetic energy of the emitted electrons. In order to do that, I need to use E equals HF, and that equals work function plus maximum kinetic energy. And so HF equals to work function plus kinetic energy max. But the work function, the HF, we know that C equals F lambda, and that implies that F equals to C over lambda. So I can then write HC over lambda equals to work function plus kinetic energy max, which meant that I can rearrange that and make kinetic energy max equals to HC over lambda, right, minus work function. Now I need to populate these values, so I can say KE max equals to 6.63 times 10 to the power minus 34 times 3 times 10 to the power 8 over 290 times 10 to the power minus 9 minus work function, and that equals to, well, with the kinetic energy, so the KE max is equal to 6.858 times 10 to the power minus 19 joules minus 4.1 electron volt. I need to convert that to electron volt. So if I divide it by 1.6 times 10 to the power minus 19, that will give me electron volt. So I'm going to get, so that gives me 4.2866 minus 4.1 electron volts. And when I take away, I should get 0.19 electron volt for the kinetic energy max. And so the answer to that will be A. Question 15. I need to find the path difference between two waves at R in terms of the wavelength of the wave. So what I need to do now is to say, well, I've got V equals 30 meters per second, and the frequency is 50 hertz. So now V equals F lambda, and therefore lambda is going to be V over F. So I can say lambda is 30 over 50, and that would be 3 over 5, and that is 0.6 meters. So how many? So if we look at path difference, so the path difference will be equal to 38 minus 30, and that gives 8 meters. Why 38? Because 20 plus 18 is 38, and take away 30, so that's 8 meters. So how many 0.6 meters can we find in 8 meters? So we have to then say, well, for the path difference will be 8 divided by 0.6, and that gives us 13.3 lambda. So the path difference will be 13.3 lambda, and the answer to that is C. So question 16, we're looking at the fringe spacing, and that equals to lambda d over s. So using Young-Slit equation, and what we need to look at now is to find what will increase the fringe spacing. Well, W, the fringe spacing, will increase if lambda increases or d increases. Also, because S is inversely proportional to W if S decreases. So we are now looking at the option, and the only option is decreasing in space separation of the double slit, and that's S. So the answer to that will be D. So question 17, what is the wavelength of the monochromatic light? Well, we are given that we've got 500 lines per millimeter, which meant that I've got 500 per means divided by millimeter, and that is 500 over, well, millimeter is going to be 1 over 1,000 meter, and that would then give us 500 times 1,000 over 1 meter. So what we've got is the line will be 500,000 per meter, and so to find D is going to be 1 over L, and that will be 1 over 5,000 per meter, which will then give us D to be 2 times 10 to the power minus 6 meter. So that's D. And once we know D, we can find the wavelength by using the Young's modulus equation, by using D sine theta equals to n lambda. And so we can then say what is lambda will be equal to D sine theta over n, but n equals 3, so we know that n equals 3, so we can say lambda equals to the D, so that's 2 times 10 to the power minus 6 sine of the angle. We are given the angle at 60 degrees, sine 60 degrees, over 3, and therefore lambda will be equal to 5.77 times 10 to the power minus 7 meters, and lambda is 580 nanometers. So lambda is 580 nanometers, and that's B. Question 18.
we need what is the refractive index of the core of the fiber optic cable.
And so in this case, we know that refractive index is always greater or equal to 1. And therefore, if you have 1 and 2, that means C1 over C2. Right.
But the question says C1, C2 is 3/5 of C1.
So C1 over 3/5 of C1, that's what C2 is. So that's 1 and 2. And to work this out, what C1 counts as C1, right? So that counts as that. So what do I get? I get 1 over 3 over 5, which gives 5 over 3, which gives 5 over 3 is 1.67. So the refractive index is 1.67, and the answer is D.
Question 19, it's asking us to find what is the path of the ray after it is incident on the surface of
X and Y. So we know that this is X,
Y surface.
Right. So let's start by saying, well, this angle is 45. That means this angle is also 45 degrees. Okay, if that's 45 degrees, but I need to find, first of all, in a question, I need to find the refractive index of this, the critical angle. So to find the critical angle, we use Snell's law, n equals 1.5, using Snell's law for critical angle, n1 sine theta of critical angle, which is sine theta 1, would be equal to n2 sine theta 2. And we know sine theta 2 will be 90 degrees at critical angle. So we're going to have, so this will be 1 times 90 degrees, sine 90 degree, which is 1. So sine 90 degrees. And so let's choose that's sine 90 degrees. And this one is 1.5 sine of the critical angle. And that becomes sine of critical angle equals to 1 over 1.5. And therefore, critical angle will be inverse sine of 1 over 1.5. And that is 42 degrees. Because it's 42 degrees, so that means that the critical angle here will be 42 degrees. So what we need to do now is to find what this angle will be. The angle here, I need to find that angle here. And to find that angle, I need to use Snell's law again. So I'm trying to find that angle here. So the Snell's law is going to be n1 sine theta 1 will be equal to n2 sine theta 2. So this is going to be 1 because it's air outside, sine 45, which will be equal to 1.5 for the glass. Sine theta 2 is what I'm looking for. So I'm going to have sine theta 2 will be sine 45 over 1.5, and that gives me 28 degrees. So that is 28 degrees. If that's 28 degrees, this is 90, right? So I can find this angle here. I can find that angle by doing 180 degrees minus 90 degrees minus 45 degrees minus 28 degrees, and that equals 17 degrees. So this is 17 degrees. So if that is 17 degrees, what is this angle here to the normal? I need the angle here to the normal. So that's the angle it's coming in to the glass. And that angle is 73 degrees. Because it's 73 degrees, 73 degrees to the normal, that is yes, because it is greater than the critical angle, 42 degrees. So this is going to be, it is going to be total internal reflection. So which one is total internal reflection? And that's D. So that is D. Question 20. We need to find 3 forces that will not produce a resultant force of 0. Well, 3 and 4, 5, if we are coming at some angle, they will produce a resultant force that is not 0. So that's okay. And likewise, 8, if you think about it, 8, I mean, if you look at 8, I mean, if that was 60, if that was 60 degrees, and that was 60 degrees, right? So if you resolve it to the, you're going to get, right, if you resolve it, so you're going to get 8 cos 60. Cos 60 is a half, so that would be 4. And you go 2 8 here, resolve this one too, and so that will be again 8 cos 60, and that's 4. That because they're going in that direction, they will produce a 0. So that is okay. Likewise, 2, 10, and 10 will produce 0. So that's okay. So the only different one is D, which will be 3, 6, and 10. I mean, if you have 3 there and you got 6 there, and then you got 10. So you can see you're going to get 9 and 10. So that's the extreme case. So D is the one that will be can never produce a resultant force of 0. Okay, so this is question 21. We need to find the extension of spring Q. If I'm looking for the extension on spring Q, I can take moment about P. So first is, what have I got? I've got a spring constant, which is 240 newtons per meter. And so I need to find the force FQ, the force on Q. Right, in order to do that, I'll take moment. Take a moment about P. So moment about P, and that indicates that. So I have 18 times 0.65. So this is clockwise, total clockwise moment equals total anti-clockwise moment. So that's what I'm doing. The total clockwise moment, this is anti-clockwise moment. Well, this one here is clockwise, so let me just show that. So that is clockwise because it's going like a clock. So that's clockwise, and this one will be anti-clockwise moment. Okay, so, and that the total clockwise moment equals to total anti-clockwise moment. So that equals to the force acting on this one on Q. So let's draw that force. That's a force here. That's FQ. So that will be FQ times 0.8 meters. So now we know we can find FQ. So FQ will be equal to 18 times 0.65 over 0.80. And so I can find FQ, and FQ will be 14.625 newtons. So that's what FQ is, 14.625 newtons. And I need to apply the Hooke's law, F equals to KE, and E is the extension called X sometimes, or sometimes it's called delta L. And so I need to find the extension here. So E will be F over K, and that equals to, the F is 14.625 over 240, and that gives 0.061 meters. And that's the extension. And so the answer to that will be 0.016, so that will be D. Question 22. What is the thrust produced by the rocket motor? We've got the mass, M, is 12,000 kilograms, and we've got acceleration, 1.4 meters per second, and we want the force because we're looking for the thrust. Thrust is the force. So what we need to do is F equals mg plus the acceleration that has been applied, ma, and therefore we can then find the common factor is m into bracket g plus a, so that's f. So f will be the m, which is 12,000 times the gravitational 9.81 plus the acceleration, which is 1.4 meters per second. So that's meters per second altogether. And if you times those two together, you should get 12,000 times 11.21, and that equals to 1.35 times 10 to the power 5 newtons. So that is the force. That's 1.3 times 10 to the power 5 newtons. So the answer is C. Question 23. We've got projectile here, and we need to find what time it takes for the projectile to return to ground. So first of all, we need to find the time it takes to get to the peak, the apex, and then we multiply by 2 to get to the time to get to the ground. So first of all, because we've got we're going to use something called here, we're going to use SUVAT. So S, we don't need to worry about that. The initial velocity, well, the initial velocity is, we've just got the velocity along the, so that's U, H, and we've got the velocity in this direction here, and that's UV. So what we're looking for is UV. So the UV is going to be, if you're using sine, so sine of 35 degrees is equal to UV over 25, and therefore UV will be equal to 25 sine 35 degrees. So that's what we need. So we want to work out the UV here, which is 25 sine 35 degrees. And next one is we want to find the A, and A is, in fact, V will be 0, and A will be 98.1 meters per second squared, and T is what we're looking for. But the U, because it's going up, so it goes like that and that. So the U is going up, so we would have to call that negative, since the V acceleration is coming down here. So now what we need to do now is to find, we can use V, so we can use V equals U plus AT. So therefore V minus U over T equals over A equals T. Now, V is 0, so that's 0 minus. Now, U is minus 25 sine 35 degrees, okay, over the acceleration 9.81, and that will become, if we multiply those two together and punch it into calculator, we're going to get 25 sine 35 degrees over 9.81, because minus times minus is plus, and that is T. So T is equal to 1.46 seconds, but the total time for coming back again down will be equal to 1.46 times 2, and therefore that equals 2.9 seconds. So 2.9 seconds. So that will be the time that we are looking for, 2.9 seconds. So the time to get to the top here, so let's use a different one. The time here is T equals 1.9646, and at the same time to get down back is also 1.46. So the time will be 1.46 plus 1.46, and that's why it's 2.9 seconds roughly. And if you look at the answer, 2.9 seconds, I get C. So question 24, we need to find out which length and radius of X will produce an extension of E over 4. Right, so we want to be using Young's modulus here. So Young's modulus, and that's E equals FL over AE. E is the extension. Right, so, but with this situation, we can cancel E and F because they'll be constant. And so we're going to have E is proportional to L over A. But we know what A is. A equals pi D. Yes, pi D. Or we might say pi R squared. So if I replace that, we get E is proportional to L over pi R squared. But pi can be ignored because it's a constant. So you get E is proportional to L over R squared. So let's write this properly. We can say E equals to K L over R squared, where I can write E L or E R squared over L equals to K. So in this case, I can say E1 R1 squared over L1 equals to E2 R2 squared over L2. Right, so if I change the E2 to be E1 over 4, so what would happen? So E1 R1 squared over L1, let's make that E1 over 4. Oh, we got R2 squared and L2. Well, so what can we do to negate the 4? Well, what we can do is to say, well, we can say E1 over 4 times, well, we can say 2. Well, we can go to 4R1 squared over 4L1. So 4R1 and 4L1 will give us E1 16R1 squared over 4 times 4L1. So the 16 we cancel, that's 16. So we need R, 4R and 4L. So if we look at the table, what gives us 4R and 4L is D. So that's D. Question 25. We have we need to find how many ions pass a point in 1 minute. Well, so we are looking for a double charge ion. So the first equation to use is NQ. So NQ equals to IT. But the Q is double plus. So double charge. So I'm going to say NQ, let's say 2 plus equals, or 2 minus rather, equals IT. So because it's a double charge ion, what we now need to do is to say, right, but we're looking for N. So N will be equal to IT over the Q, and the charge of a Q is Q but times 2. So N will be equal to current is 0.64. We got current given to us 0.64, and the time is 60 seconds. So times 6 over the charge. Charge is 1.6 times 10 to the power minus 19, but times 2 because the number of charge is double. So therefore N will be equal to 1.2 times 10 to the power 20 ions. And what gives us that? That's C. So 26, what is the time taken for the battery to charge or to discharge completely? So we need to find the time taken for the battery to discharge completely. But we got the power here. P is 200 milliwatt. The milliwatt here is basically 1 over 1,000. So we can rewrite the power to be 200 over 1,000 watts, and that will be 0.2 watts for the power. Okay, so we know the voltage here is 3.7 volts. Okay, and the charge Q is the charge is 9400 coulomb. And so what we now need is to write the equation Q equals IT, at the same time P equals IV. So if I make the I the subject, so I is P over V, and therefore Q equals PT over V. I need to find time, so T will be equal to QV over P, and we know Q is 9400 times 3.7 divided by the power 0.2, and what do we get? So T will be equal to 131.1739.005 seconds, sorry. So that is seconds, but we want it in hours. So we have to do T will be equal to 173,900 over 60 times 60 to convert it to hours. So that will be 48.3 hours. So that's 48. And what gives us 48? B. So the answer is B. 27. We need to, what is the total resistance of the combination? And we are given that the resistance is equal to rho L over A, and they have same resistivity and same length, so those we cancel out, and so resistance is directly proportional to 1 over A. But A, when we look at A equals pi d, right? So A is pi d, but d is r over 2, so area is pi r squared. So what we want to do now is to say the capital resistivity is proportional to 1 over r squared. If that's the case, what we can do is to say, well, capital R squared equals K. Therefore, R1 squared must equal to R2 squared. Now, what we need is
the diameter is what it is y is twice that of x.
So
Y is
twice of x. So we can say R1 squared is equal to capital R2 to R1 all squared. So now we can say R1 squared equals to R2 4 R1 squared. R1 cancel R1 squared cancel R1 squared. So we're going to get, R1 is equal to R2 4.
So this is going to be 4
R1. So R1 is going to be 4 R1 for the R2. So R2 is 4 R1. Okay. So what we now need to do is the total will then be R1 plus 4 R1, and that will be 5 R1. So the total would be 5R. So what has 5R? D.
Question 28. A voltmeter is used to measure a potential difference for a component X. Which row gives the position and ideal resistance for the voltmeter?
So if you have a component X like that, you always connect a voltmeter parallel to the component X, and the voltmeter will have a higher or infinite resistance to stop the current flowing through it. So to stop current flowing through it. So that's what you would have for a voltmeter. For an ammeter, it will be connected in series, and it will have a very low resistance because you want current to flow through the ammeter but not through the voltmeter. So the answer to this one is basically C.
Question 29. For a simple harmonic motion, we want the displacement time graph and we want the acceleration time graph. So the displacement is x equals to a cos theta, and the acceleration a is going to be, well, if you differentiate first, it's going to be minus a omega sine theta, and if you then differentiate, that's velocity, by the way, so that's the velocity. And so if you differentiate again, you're going to get minus a omega squared cos theta. So you can see that if you sketch the displacement x with time, because it's cos, it will begin like that, right? If you sketch acceleration, and well, it's cos, so it will start from there. So if you look at cos is the pi, the lag, the difference here is pi radians. So this is acceleration time graph, and that's displacement time graph. So the difference between that and there is basically what we call pi radians, and that's where you have here, so pi radians. So the answer to that one is going to be D. D is the pi radians. Question 30. We have an object of mass 0.15 kilograms. So M is 0.15 kilograms. Perform a simple harmonic motion. It oscillates with amplitude of A is 55 millimeters, and that would be 55 over 1000 meters
which is 0.055 meters. So that's the amplitude. With a frequency is 0.8 hertz. So what is the maximum velocity? What is the maximum value of its frequency, of its energy? What is the maximum value of its kinetic energy? So what Ke max is equal to a half mv max squared. But we know that V max is basically equal to omega A. And we know what omega is. That's 2 pi f, and that's A. So if I square V max squared, I would have to square 2 pi f A all squared, and that would be 4 pi squared f squared a squared. So the kinetic energy is going to be Ke max would be a half m 4 pi squared f squared a squared, and that will give 2 m pi squared f squared a squared for the Ke max. So what I can do is plug these values in. Ke max will be 2 times 0.15 times the frequency, which is 0.8 squared, times pi squared, times 0.055 squared. And when we times all that together, we get 5.7 times 10 to the power minus 3 joules. So that's the maximum kinetic energy. And what value is that? That's A. Question 31. Which graph shows the gravitational potential energy of a simple pendulum varies with displacement s from the equilibrium position? So what we have is a simple pendulum. So if you actually plot a graph like that, if that's s, and that's energy due to gravitational potential, when s is 0, you can see that the potential energy will be 0. And when the s is at maximum, potential energy is maximum. It's also is reflective over there as well. So the answer to that will be D.